Hello, I'm Geneva Bowling, and I'm here to present my Lab 1 constant velocity presentation. The purpose of this experiment is to analyze the motion of the observed object that is moving at the same speed without changing direction, using Tracker to extract the object's position and time, and using GlowScript to predict the object's position and time. For fundamental principles, we will be using Newton's second law, which is force equals ma, velocity update position to find the velocity, and then the position update formula to find its position. For this procedure, we are going to record the motion of the object rolling across the table in the positive x direction, import the video into Tracker software, and track the position of the object at the set timestamps, edit the starter code in GlowScript to create a predicted model for the object's motion, compare the position and versus time graphs of the experimental and predicted object. As you can see here, this will be the setup, the system will be the moving object, and the surrounding is the desk. As a result, this is our position versus time graph. The experimental graph is a little rigid, that's probably due to errors, and the predicted model is a straight linear line. And we will explain how this happens. As you can see, this is my Tracker software, and you can see the moving object, which is a self-tanning mousse bottle. At 0 seconds, as it starts to move, you can see the bottle is moving across the x direction at the positive direction, and over here it makes somewhat a linear line. The breakdown over here, the system is the Tanologist self-tan mousse, or the bottle, and the surrounding is the desk. Friction is negligible, is stated in the lab report. Gravity is also not affected since gravity only worries about the y direction, and the air resistance is negligible. Initial conditions, position is at 0.29 meters in the positive direction, velocity at 1.71 meters per second in the positive direction, and time is 0 seconds. This is my GlowScript code. As you can see here at line 32, ball.m, which is ball's mass, it is set as 200 grams or 0.2 kilograms, and then the ball's position is at the vector. That is my initial condition, and then ball's velocity is also, again, the initial velocity that I studied. It will start at 0 seconds, as I said, and then the delta t, or the timestamp, will be at 0.033 seconds. And this is where all the magic happens. In line 57, f net equals 0 because velocity is a constant. And in line 60, if f net is 0, f final equals f initial, which means that it is constant. In the position formula, which is underneath, the position is determined by the constant velocity, which is important to see how far the ball moves over delta t. In the GlowScript model, you can see that the blue ball has moved away from the origin. In the position versus time graph, you can see it's a positive linear slope, and in the velocity versus time graph, it is constant. Possible sources of errors: the table surface is not perfectly smooth, the air resistance and friction is not ineligible. Calibration scaling anomaly, I did set it as 1 meter. While the number is mathematically larger than the real world dimensions, the overall relationship remains unchanged. Velocity remained constant, the position time graph is a clean straight line, and my computational model still aligns beautifully with the experimental data. For future experiments, this could be easily corrected by using the object of known length, such as a ruler. Also, the half-empty bottle caused the velocity to not be constant. For similarities and differences, you can see that the experimental data is a little rigidity, and also at the starting position it seems to accelerate and then move in a constant velocity. The predicted model is linear, however there is something little going on in the starting position, but it is perfectly linear. What if the axis is flipped? The ball will move at the negative x direction. You can see in the position time graph it is going down, while the velocity versus time, it is constant, however velocity is now negative. Is it possible to predict how many pushes and pulls? No, it is not possible to predict how many pushes and pulls because F net is just the sum of all forces. You cannot determine the exact number of individual forces from data alone. If you know the situation, however, you may know how many individual forces are in the system, like gravity, friction, and etc.